Good afternoon, dear ladies and gentlemen. I thank the organizers, first of all, for giving an opportunity to give a talk. The talk will deal with the switching rate computation for full-scale micromagnetic simulations as opposed to the macrospin approximation. This is a brief outline of my talk. Number one is basically this slide. And then I will quickly go through two analytical methods and Langevin dynamic simulations, which are the direct method to compute the switching rate. And then I will concentrate myself on numerical methods which employ the so-called climbing paradigm. These are the energy bonds method and forward flux method. And I will basically speak about adaptation of these both methods to full-scale micromagnetic modeling. Now we are simulating the simplest possible system, which has two distinct energy minima. This will be ellipsoidal nanoelement single layer with two equivalent energy minima by mx plus minus 1 and with a range of energy barriers from low to intermediate. And we work in a micromagnetic paradigm, meaning that we discretize each element into cells in plane with the cell sizes about 3 × 3 square nanometers. We have already performed extensive research on this system in the macrospin approximation here, and you can look at this paper to find all the results there. Now we have first two analytical approximations. The maybe most famous one is the Arrhenius-Van Hoff law, where you evaluate the switching time just as the product of the inverse attempt frequency and the exponent of the energy barrier. It is most widely used, but still I would say the worst approximation available, because it does not take into account actually nothing except the energy barrier. It does not take into account damping. This is especially bad because without damping you don't have any switching in thermodynamics. It does not take into account the energy landscape around the settled point, possibility of reverse transitions, and of course a possibility of non-homogeneous magnetization reversal if we are in some micromagnetic framework. Some of these drawbacks were corrected by Melnikov and Meshkov in 1986. They have obtained a general expression for an arbitrary damping. It was really a big success, solution of the famous Kramer's problem. They could compute the flux over the saddle point, and this led to the introduction of this factor, depopulation factor, and to these two factors, damped and dampened saddle frequency. So landscape around the saddle point is fully included. What still is missing in this analytical approximation is obviously again the possibility of reverse transitions and non-homogeneous magnetization reversal. But this is still the analytical standard to be compared with. Now, among direct simulations, we obviously have the Langevin dynamics as a method of choice. You simply, or not simply, because it is a stochastic differential equation, you solve the Landau-Lifshitz-Gilbert equation with a fluctuation field. And this approximation, this method obviously works for small energy barriers only because the switching time depends exponentially on the energy barrier. And this is our golden standard. It is possible to perform Langevin dynamics for the smallest element with 9 kT energy barrier. And you have this result, a nice exponential distribution of switching times. And this is a dispersion of this distribution. So this is our reference switching time for other methods. Now I will concentrate on more advanced numerical methods which are able to cope formally with the energy barrier of any height. And we start with the energy bonds method introduced recently by, well, not recently more, but still during the last time by Wong and Vischer. And the idea is if you have an energy landscape with a corresponding saddle point, then you divide your energy landscape into energy levels. And at each stage, you do not allow your system to go below a certain energy level. So you just reject any attempt of the Langevin dynamics trajectory to go below a certain energy. This way, you get energy histograms like this. So these are Bohn's energies. And your problem is that in order to calculate the switching time from here to here, you have to take the switching time when the system is at the level high enough to find sufficiently many transitions with the usual Langevin dynamics. And you should divide the switching time by the product of transition probabilities, which is simply the relation of the histogram you obtained by the Bohn's energy y divided by the Bohn's energy y plus 1. So the problem is how to compute these transition probabilities. For the macro spin, as I said, it is quite simple. You can simply divide this area by this one. But if you start your micromagnetic simulations, you quickly discover that the method does not work for micromagnetic framework, because for the energy barrier of 9 kT, you quickly have energies around 100 to 200 kT. After 10 seconds thinking, you realize that the problem is the exchange energy, because the exchange energy gives the overwhelming contribution to the total micromagnetic energy. It is about the same 100 to 200 kT. And the dipole energy also does not behave itself well, simply because there are many internal modes in this system. So this is once more this conclusion. So you have to invent something to make the method at least approximately work. Okay, the idea is we use as the Bohn's energy that part of the magnetodipolar energy which corresponds to the homogeneous magnetization state. It is with the wave vector 0. And we do this because this mode with k equals 0, meaning that this is the dipolar energy of the average magnetization, is the indicator for switching. Everything is okay with the switching. It is well, reasonably small. And the only problem which remains is how to define these probabilities. Initially, the idea of Wong was that you can just compute the ratio of these integrals, as I said, but this is no more true for full-scale micromagnetics, because now this is the partial energy, only dipolar energy for k equals 0, so it does not abide the Boltzmann statistics. So we use the direct definition of this transition factor as the ratio of the time the system spent above the I plus 1 level divided by the time the system spent by the level number y. Then the method works reasonably. You have the product of transition probabilities, which exponentially decays with the number of level. You have number of switchings, which exponentially increases with the number of level. So you have here the nice plateau. But the time you compute this way is unfortunately around, in this example, is around 3 times smaller than the time it should be according to the Langevin dynamics. So the reason should be found out. Again, it has to do with the fact that the system or the energy which you declare as the Bohn's energy is not more the total system energy. So the reason is that your energy for Langevin dynamic simulation can be smaller than the system energy for the initial state. So this is shown here. This is the energy for the initial state, and this is your Langevin dynamics fluctuation. So you have to introduce an additional factor, time, which the system spends for the dynamical energy larger than the statical energy. And after doing this correction, you arrive at a very comfortable time of 1.77 compared to the 1.8. So the method works at least for small energies. Now, after all this introduction, the further flux sampling is nearly simple. You probably know the main paradigm. You just evaluate the flux from the basin A through the interface lambda 0, and then conditional probabilities to find a transition from the interface lambda y to the interface lambda y plus 1, and the product of this flux and these probabilities gives you the time. We use in our approach, in our version of the forward flux, not the moment projections, but we use the energies again. And these are the energy interfaces placed in the energy space. For the same reason, interfaces in the total energy space are not suitable due to the overwhelming contribution of the exchange, and we have the same solution. We place interface equidistantly in the dipolar energy space. You have to watch for the optimal position of the interfaces near the saddle point, because you can place the interfaces very unluckily to get a very large simulation time even in this case, but optimal position allows you to reduce simulations time over an order of magnitude. And the method works very well. You can see it on the independence of the probability on the interface position, which should be for the optimal forward flux. Fine. Now let us compare the results. You have here the analytic approximation and 1 point for the Langevin dynamics. It's here and 2 curves for 2 methods. It is reasonable to divide all that by the analytical approximation, and for our 2 methods, 2 numerical methods, you get 2 curves, the yellow one for the forward flux and this one for the energy bonds. And you see that the energy bonds method performs actually not good. It coincides with Langevin dynamics for small barriers, but for large barriers, simulation switching times become unreasonably small. This is most probable due to the fact that energy bonds uses an artificial condition. Energy is larger than energy bonds at each stage. And this is a large disturbance of the energy landscape and of the equilibrium thermodynamics as a consequence. FFS delivers correct switching times, and in this region of energy barriers, this time is smaller than the analytical times, because the analytical approximation does not take into account homogeneous modes which deliver additional energy to the system to be switched. And these are our general conclusions. We have optimized numerical methods for full-scale micromagnetic simulations. Energy bonds refuses to do its work due to the disturbance of the thermodynamic equilibrium by artificial energy levels, but forward flux method with the interfaces positioned in the K0 dipolar energy space provides most reliable and accurate results. Thank you very much.